Okay, in this problem, we are going to solve, or during this time, we're going to solve the third problem in your example problems that looks like this. Okay, where we have the battery operating the circuit as shown. So it begins, I guess, on this here. We were taking a look at what is the way that we can connect these together to give us our lowest amount of current passing through and our greatest amount of non-zero current passing through. So we want to make it as small as possible and as large a part as possible. We have a 10 ohm, 30 ohm, 20 ohm, and 100 ohm resistor all connected. So the first thing we would recognize is that if we want it to be as small as possible, right? So as small as possible from the equation that voltage is equal to current times resistance, we would want our current, which is voltage divided by resistance. For our total current, we want the resistance to be as high as possible, right? So to get the greatest resistance, we want this connected in series so that your total resistance would be equal to 100 plus 20 plus 30 plus 10, or the 160 ohms. So you don't really need to know that. It just is a matter of you connecting these in series. So it asks you to draw a picture of all these resistors in series, and it doesn't really matter how you draw that, as long as each one of these resistors can go through one path, all the current must pass through them. Which means then when we get to the second half of this problem, if we want the largest resistance or largest current as possible, that current, again, total current is going to be your total voltage divided by your total resistance. So we want this number, because we're dividing by it, to be as small as possible. Therefore, to make it as small as possible, we want it to be in parallel. So we want each resistor to be on its own branch in a parallel circuit. So just asked to do that in conceptually. You don't have to do any calculations. You can certainly check and verify that the calculations turn out to be that this will give you the highest possible and the lowest possible current that you need in each one of those situations. Moving on to this next part, I want to work on this because it's this network circuit and how we add all of these resistances and so together, and what does that mean with voltages and current. So in this case, we want to know the current through the 10 ohm resistor, the total power consumed or used by the circuit, and then we'll talk about the energy. So in this one, I'm going to switch over to our whiteboard. Excuse me. And the first thing you want to do before you even start thinking about everything is think in terms of equivalent resistance, right? So if this current comes out of our power supply, at this point it's going to split up. So I'm going to draw those as two separate lines. Some of it's going to go in this direction. Some of it's going to go in this direction. They will come back together here, right? And travel the rest of the way through the circuit. So what we do know is the total current is what travels through resistor 10. So I10 is equal to I total, right? Because it must go through 10 to get back to the battery. So what I'm going to do is draw equivalent resistances to begin with, which means I'm going to eliminate parts of the circuit to put in only one resistor, keeping everything else the same. So I'm going to keep the 100 ohm here. I'm going to replace these two with one resistor. And they come back together, and here's our 10 ohm. These two together are in series, right? They come together to make this resistance. So that's a series circuit. So your R, we'll call that, I guess I can give each one of these a resistance number just to allow us to number all of these. So I'm going to call this 1, 2, 3, and 4. So then I'm going to call this R2, 3, because it's the sum of 2 and 3 together, is going to equal R2 plus R3. So R2, 3 is going to be 20 ohms plus 30 ohms. R2, 3 is equal to 50 ohms. So the equivalent circuit would be that if I were to build that to make something that would have 50 ohms here, right? The 110 are still the same. I'm going to do another circuit, calling it an equivalent circuit as well, where I'm going to eliminate the parallel part right there. So I know that's parallel because at this point, I have to choose, do I want to go through the 100 or the 50? And that's all that I'm choosing between. So I go along and I'm going to eliminate those two into one, which leaves the 10 still there. So this is my 10 ohm. These right here come from this section. That's making that resistor. That resistor total, I'm going to call R1, 2, 3, comes from a parallel. So 1 over R1, 2, 3 equals 1 over R1 plus 1 over R2, 3, which I just calculated, right? So that's going to be 1 over R1, 2, 3 is equal to 1 over 100 ohms plus 1 over 50 ohms. That's going to give us 3 over 100 ohms. So reciprocating both sides, right? So reciprocating both sides, we get R1, 2, 3 to be 100 ohms divided by 3, which is 33.3 ohms. So now what is my R total? So now at that point, I have a complete series circuit, right, which is 2 resistors. Oops. If I label this one, 33.3 ohms. So now I can say my total resistance, getting it down to 1 resistor, R total is going to be R1, 2, 3 plus R4. So this now comes from the series. So our total, follow the series rule, is going to be 33.3 ohms plus 10 ohms. So my total resistance is 43.3 ohms. Okay. So now when I look at all of those circuits together, what that means is no matter how I build this circuit, if with any one of those 4 circuits would cause the same total current to come out of the battery in the same amount. So if I go back and I trace this current, right? So remember, if we go back and we take a look at the path of the current, we see that in this circuit, that total current comes out. Total current comes out and goes through R1, 2, 3 and R1 and R1, 2, 3. Sorry, R1, 2, 3 and R4, right? Over here, that total current is coming out and it's going to split between the R1, R2, 3, and then come back together and go through, you want to do that, go through R4, right? But up here, we definitely notice that again, it's going to split between these 2 paths right in here. Okay. So going back to our initial thought, what is the current that goes through the 10 ohm resistor? That's going to be equivalent to the total. So now that I know V total is equal to 12 volts, R total is equal to 43.3 ohms, I can find I total. I total is going to be V total over R total, which is going to be 12 volts divided by 43.3 ohms. My total current passing through then is 0.28 amps. Okay. So I know the 0.28 amps is going to come out of the battery and go through each thing. Now for power, remember for the equation for power, power is equal to, in electricity, current times voltage. So my total power is going to be my total current times my total voltage. So that's going to be 0.28 amps times my total voltage of 12 volts to give my total power of 3.36 watts. Now with our total power, remember that the unit of a watt is equal to a joule per second. So for the last part where it says, how long would it take to provide 10 kilojoules of energy? We're looking for the time in this case. So we want to know how long does it take to get 10,000 or 10 kilojoules. So that's 10,000 joules. So in this case, we want to multiply by something to get rid of joules and change it to seconds, and that's where the power comes in. So we just calculated this to be 3.36 joules per second. So putting that number in here, 3.36 per 1 second, joule per second, we will get in seconds the amount of time of 2,976.2 seconds. If you want to convert that to hours, then you can say 1 hour is equal to 3,600 seconds. So you will get the amount of time to be 0.82 hours. And what that means is that circuit will use up that much energy in 0.82 hours when connected as is. Okay? So just some things I want to point out is if I were to go back and try to find voltages and things, all of this current goes through each one of these sections, right? So knowing the current through each one of these resistors, I can then find the voltage of each one of these resistors. Since this came from parallel, this one right here, that means V, coming back over here, I could say V1, 2, 3 is equal to V1 is equal to V2, 3, because that's where it comes from, the parallel section, right? I can say here that V1, 2, 3 plus V4 is equal to V total. Just some things to think about with voltage. Because it's in series, not in series here, we can say in series, I total is equal to I1, 2, 3 is equal to I10. This is not necessary. This is just for future taking a look at each circuit. If I go back to this circuit, from that circuit, since it's in parallel in this section, I can say that I1, 2, 3 is equal to I1 plus I2, 3. right? So the goal here is just to be consistent in your subscripts and what circuit you're looking at. So you can see as you build backwards. Over here, the parallel part is this part, and we would say that V1, right? V of resistance 1 is equal to V23 because they're in parallel. So once you find V23 here, you could maybe use it to find V1, which would allow you to get current 1. And what we know in current, we would say over here that I2 must equal I3 because they're in series. I total equals what goes through bulb 1 or object 1 plus I2 or I3, right? Because they're equal. So we'll just say what goes through I2 equals I10. So those are some things you can take a look at as you look at this circuit and look at all the equivalent things that happen throughout that circuit.